Hi, in this video we're going to look at heating and cooling curves. Heating curve. This is what a heating curve looks like, and let's use water for an example, right? We have this. And this is solid state, liquid state, and gas state. This side is temperature, and this side is energy. At 0 degrees is solid, and at 100 degrees, 100 degrees over here, it becomes gas. And now we call this process over here melting, and we call this process over here vaporization. And now this should be a straight line and not a bent line, so let me draw this better. And here, this curve might look familiar because this is the states of water. And if we say during melting and vaporization, temperature stays constant, yet the energy increases. As you can see from the chart, the temperature did not increase, but the energy increases. This energy is used to break intermolecular forces during melting / vaporization. So as we increase temperature, as we go along this line, first it goes from the solid state, and at one point you need to break all the intermolecular forces in order for the whole thing to become liquid state. And now in this, it's a combination of solid and liquid, right? You can't have this will be a combination of solid and liquid. And in order to make the whole thing liquid, the extra energy, this much of energy, is used to break the intermolecular forces between the solid molecules in order to make everything liquid. Again, from liquid to become a fully gas, you need to break all the intermolecular forces in order for that to happen. And now, what is the difference between vaporization and evaporation? Vaporization occurs at boiling point, and that is like boiling water. That is vaporization. And now, evaporation, it happens below boiling point, and that is leaving a bottle of water in a classroom overnight. When you come back the next day, there will not be as much water in there because some of it has evaporated, yet the room temperature has not reached boiling point yet. Now our second chart is a cooling chart. And just as you might have expected, it looks just like a heating chart, except it's opposite. Cooling curve, CURV there. Now this is a cooling curve, and again, go from gas to liquid to solid, and this, we call this condensation, and this is freezing. From gas straight to solid, we call this deposition. And again, if we're going to go from solid straight to gas, we call that sublimation. I guess this is how heating and cooling curves look like. Now let's look at some more vocabulary. We have vapor pressure. Vapor pressure is the pressure exerted by a vapor at equilibrium with its solid or liquid at room temperature, which is 25 degrees C. That's something good to know. Room temperature is 25 degrees C. And now, basically all you need to know right now is that this basically means pressure. Right? Your problem if it asks you for water pressure, vapor pressure, just look for the pressure, and that is the vapor pressure. And now, why does vapor pressure increase as temperature increases? Well, that is because as temperature increases, more particles have kinetic energy to become vapor. The more vapor means the more collisions, which means more vapor pressure. Now here's two vocabulary terms that you know. First we have volatile, and that is evaporates easily. This means it has a low boiling point, and as well as weak intermolecular forces. Now, for example, this is rubbing alcohol. If you pour rubbing alcohol, it evaporates very quickly because it has a low boiling point and the intermolecular forces are weak. Now, second is non-volatile, and that is strong intermolecular forces, which results in high boiling point, which also results in does not evaporate easily. And this is the opposite of volatile. And that is all you need to know for heating and cooling curves. Again, we'll be looking at these again and doing some more advanced problems when we get to Unit 9. Thank you for watching.